Hello, everybody, and welcome to Electron Configurations and Periodic Table by Gaddafini. So, first we're going to talk about valence electrons. So, first, the valence electrons are the representative elements, and the representative element is basically just an element at the top of each group, like carbon and nitrogen, for example. Those are representative elements, they represent their group. So, elements in a group or a column have similar chemical properties because their valence electrons are in similar configurations. So, for example, all elements in group 1A will have one valence electron, all elements in group 2A will have two valence electrons, and so on and so forth. Number two, valence electrons in the periods. So remember, the period corresponds to the highest energy level shell that each atom in that period has. So the period or row in which an element is found tells us in what energy level its valence electrons are found in. So for example, all elements in period 1 have valence electrons in energy level 1. And for all the elements in period 2, they're going to have all their valence electrons in the second shell, and so on and so forth. All right, so pop quiz. How many valence electrons does each of the following elements have, and what energy level are they in? So pause the video, try to answer these, and I will get back to you with the answers. Okay, so for number one, potassium, we can see that potassium is in group 1A, which means it has one valence electron. And we can see it's in period 4, which means it's in energy level 4. For carbon, carbon is in group 4A, which means it has 4 valence electrons, and it's in period 2, which means that those valence electrons are located in the second energy level. And finally, you have lead. Lead is also located in group 4A, so it has 4 valence electrons, and it's in period, it's in period 6, which means that those electrons are going to be found in energy level 6. And the rule that basically the group number corresponds to the amount of valence electrons is mostly true for the 1A, 2A, and 3A to 8A. With the transition metals and the intertransition metals, it could be a little different, but as long as you know the ones through 1A, 2A, and 3A through 8A, you should be good. All right, so now we're going to talk about the S, P, D, and F block elements. So elements are placed in blocks based on highest energy orbitals to fill with electrons. So for example, the elements in groups 3A through 8A, excluding helium, are going to have these particular p orbitals be the highest energy orbitals that are going to fill with electrons. And something really important to note is that when you're going from when you're in period 4 and you're going from the S block to the D block, you have to do n minus 1. See how it goes 4 to 3, 5 to 4, 6 to 5. And the same rule goes from here. If you're like from the D block to the F block. So if you're in 7S, so period 7, and you want to go down to the F block, which you'll see later as we add electrons, we're going to have to go down here. You're going to have to do n minus 2 to get to here. So from 7 down to here, it's 5. So that's 7 take away 2 is 5. And 6 to 4 is take away 2. So that's something pretty important to keep in mind. And other than that, as you practice, you'll get used to these general patterns. So they'll just become second nature. But this is going to be really important because as we fill up electron configurations and everything like that, we're going to start plopping electrons into specific orbitals in certain energy levels one at a time. So it's going to be important when we get down to here that we know how to basically put them in the right energy level in particular orbital. So yeah. So I think the best way to learn this is just by doing examples, and I'll walk you through a few before I give you some practice ones to do so you can uh, become a pro at this. So first we're going to look at magnesium. So when filling up these electron configurations, we're going to write the full one and the abbreviated one. You're going to go from left to right and from top to bottom. And I'll show you what I mean in a second. So magnesium, number 12, right over here. We're going to start up here at period 1, and it's going to have one S2, because you're in the first energy level, S orbital because you're part of the S block, and you have 2 electrons, 1, 2, going into it. Come down because we went left to right, and now we're going top to bottom. Now we're in energy level 2. We're still in the S block, so we're going to have S. And now we're going to put 2 because 1, 2. Now we keep going left to right. Now we're still in energy level 2, but now we're in the P block. And to get to magnesium, we need to fill 1, 2, 3, 4, 5, 6 electrons, or this P block up with 6 electrons. So we're done with this row here, down to the next row. And we're in energy level 3 now. Now we're in the S block, so S orbital is being filled with 1, 2 electrons. And at this point, we're at magnesium, so we stop and we're good. And that's the full electron configuration. Now to write the abbreviated, abbreviated electron configuration, you're first going to have to determine what magnesium's inner noble gas core of electrons is. And for that, all you have to do is just go back to the nearest noble gas to magnesium. Don't ever go like forward. It's always going back, because neon represents, we write it like this, the electrons that are least likely for the particular atom of magnesium to react, because they're in that noble gas inner core. This is like super stable. The electrons in here aren't really going to react naturally. So you always want to go back to the closest noble gas, and that's going to represent the inner core of electrons that's not really going to react. So for example, if we were in sulfur, its noble gas core would still be neon. You have to go back because it represents all these core electrons that really aren't going to react. The ones in the valence, though, will. So back to magnesium, we determined its noble gas inner core, which is neon. So we wrote that in there with brackets. And then we just write the rest of the electrons like we would normally do. So we're back to period 3. And we have 2 electrons in that s orbital. So it's going to look like neon 3s2. So these ones here are all being placed inside the noble gas inner stable core because they're not going to really react too much. So we represent it like this. And we got these valence electrons, which are more likely to react. And this explains why the Lewis dot structure for magnesium looks like this. Just these 2 valence electrons, which are going to pop off and do their own thing. And also explains why magnesium has a 2+ charge and everything like that, because these 2 electrons are going to be the ones that react. And it's a metal, so it's going to get, for ions this is, and this is for more like molecules. So yeah, so that's basically magnesium and all the connections with everything. It's kind of beautiful how like it all kind of works together. There's always going to be wacky exceptions, but this is something to take note of, how this all kind of connects and works and makes sense. So if this all makes sense, then you're definitely doing it right. If you get something whack and it doesn't all line up, then it could be an exception, or you just got to keep practicing. So let's move to the next one. All right, so the next element we have is lead, which is all the way over here. So let's get this done. So we're going to start again up here with 1s2, move down to 2s2. Now we're going to go to 2p6, move on down to 3s2, now 3p6, and now we're going to get into 4s2. And now remember, now we're in the D block, so we have to do n-1. So we're in energy level 4, but now we're in D, so it's n-1, so we're at 3. So 3, and all these are getting filled up with electrons, so 3d 10, because 10 electrons can be held here. Now we're back into the P block, so this n-1 rule is only for the D block. So now that we're in P block, forget about it. We're back in energy level 4. We're at 4p6. And now we come over back to 5s2, like how we would normally do. We see that we're in the D block, so we have to do n-1 again. So 4d10. Back into P block, so forget that n-1 thing. We're back in 5 now. 5p6. And now we're going to get into energy level 6 with 6s2. And now this is very important. This is what we were talking about earlier. This star thing here might not be in your periodic table. This is something you have to know, that when you get down here, in reality, the periodic table doesn't actually look like this top block part. These things are really shoved into here. So you have to come down here when you get to this point, down over here to the F block, which remember was n minus 2. We have to take that into consideration. So if we're at 6, we're into 6 minus 2, which is 4. So now we're back into 4. So I'll write that over here. Sorry, it's getting cramped and messy a little bit. And then we're going to count all these electrons being placed in this particular F orbital in this energy level, which is 14. And now that we did that, we're going to come back up, bam, back to 71. But now, remember, we're in D block now, so we have to do 6 minus 1, back up to 5. So 5D10. And we keep on going all the way through. And now we're at, look at that, we're finally here. So 6, because we're back in the P block, we don't have to worry about these weird energy level rules. We just do 6S, and there's 2 electrons until we get to PB. So that's what this is. This is the full electron configuration, and I'll show you the abbreviated one real quick. So we see lead. Lead's right here. For the abbreviated one, we need its noble gas core. So we look back to the nearest noble gas, which happens to be Xeon. So we write that in brackets like that. And then we just start from here. So there you go. All right, so the next walkthrough, uranium. And there you go. This is the full electron configuration for uranium. And in order to do the noble gas configure or abbreviated electron configuration, and there you go. There's your abbreviated electron configuration for uranium. All right, now you got to try some, and that's it for SE. All right, now we're going to do lawrencium, which is right over, right here. So there's your full one. So there you go. And that's for lawrencium. And finally, we're going to do boron. So boron's pretty easy, so it's a nice way to end off. And